Okay, thank you. Go ahead.
Yeah. So I'm happy to introduce Marcus, who will tell us about categorical decision theory, please.
All right, so thank you all very much for being here, and thank you very much to the organizers for inviting me and for putting this together. So I'm going to start by just briefly explaining what decision theory is about. So decision theory is a branch of theoretical economics which studies the problem of decision-making under situations of risk or uncertainty. Now, there are two different branches of decision theory. There is normative decision theory and descriptive decision theory. So normative decision theory is kind of interested in the philosophical question, how would an ideal rational agent ideally make decisions, right? How should you make decisions? Whereas descriptive decision theory is more interested in the kind of psychological question, how do actual human beings actually make decisions in reality? So this talk is going to be about normative decision theory. So I'm not making any claims about actual human behavior or actual human psychology. So we're interested in the question, how should a rational agent make decisions in a situation of uncertainty? Right now, as most of you have probably heard, back in the 18th century, Daniel Bernoulli proposed a pretty convincing answer to this question. He said that a rational agent should choose the action that maximizes expected utility. And this is more or less the sort of like default view. It's a consensus view, but you could sort of ask the question, why? Right? What's so rational about maximizing expected utility? So one answer to that question was given by von Neumann and Morgenstern in 1948. So they imagined a situation where the agent has to choose between different lotteries, which assign objective known probabilities to the outcomes. And they said that if the agent is going to choose rationally between these lotteries, then she has to maximize expected utility because that's the only procedure that satisfies certain axioms of kind of rationality or internal coherence. But then, of course, you could ask the further question, well, what about a situation where you don't have objective known probabilities? And shortly after von Neumann and Morgenstern, Savage answered this question. He said in this situation, the agent should sort of contrive some subjective probabilities representing her subjective beliefs about the world, and she should maximize expected utility with these subjective probabilities. All right, so let's just briefly take a look at the Savage model. So Savage proposes a model with the following components. So first of all, there's a set S of possible states of nature, okay? And we suppose that the true state is unknown to us. So S represents all the information about the world that is unknown to the agent. It's the source of uncertainty in the model. There's also a set X of possible outcomes like consumption bundles or the ways that somebody's life could go. And we suppose that these are the only things that the agent ultimately cares about. All right, so every alternative, every course of action, every strategy is represented as a function mapping states into outcomes, and Savage called these functions acts. And so the way we suppose that the things unfold is that the agent chooses some act alpha, okay? And then after she makes her choice, the true state of nature is revealed. And if the true state turns out to be S, then she gets the outcome alpha of S, okay? And so given this setup, the agent wants to choose the best possible act, right? That's her problem. So let X to the power S be the set of all logically possible acts, right? All functions mapping S into X. And we suppose that there's a weak order on this set. So that means a complete transitive binary relation, which represents the agent's preferences. So for any act alpha and beta, basically the statement alpha is preferred to beta. This means that the agent prefers alpha over beta ex ante. So given a choice between alpha and beta, she would choose alpha. So Savage's theorem, this is a little bit weak. Savage's theorem says that if the agent's preference order satisfies 6 axioms, which again encode some notions of internal coherence or rationality, then there exist two things. First of all, a real valued function u on the set of outcomes, which we interpret as a kind of a cardinal utility function. And second of all, a probability measure mu on the state space, which together provide a subjective expected utility representation for the agent's preferences. And what does that mean exactly? It means given any two actions, alpha and beta, the agent prefers alpha over beta if and only if the mu integral of u composed with alpha, so in other words, the expected utility of alpha, is greater than the expected utility of beta. Okay, so this has a nice kind of psychological interpretation. Intuitively, the utility function u describes the agent's desires concerning outcomes, whereas the probability measure mu represents her beliefs about the unknown state of the world. Okay, so this is kind of the benchmark result in modern decision theory. It's a very important result, but there are sort of several ways that we might want to extend Savage's framework. So let's start with two. So first of all, in the Savage framework, the state space is just an abstract set, and acts are just abstract functions. There's no structure, right? But there are many situations where we might want to introduce some additional structure. For example, we might want the state space and the outcome space to have a topology or a geometric structure, and then we might want acts to be like continuous or smooth or something like that, right? At the opposite extreme, there may be situations where we don't know anything at all about the state space, right? The agent is confronting uncertainty. She sort of has some vague idea that there are like some states and outcomes, but she doesn't really have the ability to sort of specify the state space in a very concrete way. And we'd like to sort of have something like the Savage theorem in that setting as well. Okay, so the idea of this project is to reformulate the Savage model using ideas from category theory to obtain a model which satisfies these desiderata. So roughly speaking, so by the way, I'm going to be using some notation. And this is sort of probably not totally standard notation, but I like it. I hope it makes sense to you. So for any category C, C with an O, that represents a set of objects in C. Given two objects A and B, C with the arrow over it, AB, that's a set of morphisms. I'm going to represent functors using double arrows like this, and I'm going to represent natural transformations between functors with kind of triple arrows like this. Okay, and for simplicity in my examples, I'm going to be focusing on the category of sets and functions. But the theory also applies to basically all of your other favorite concrete categories, like the category of measurable spaces and measurable functions, or the category of topological spaces and continuous maps, the category of differentiable manifolds and smooth maps, and also importantly, it's supposed to apply in many abstract categories. All right, so let's get started. So suppose that C is some category and let S and X be two objects in this category, okay? So the interpretation here, as the notation suggests, is that S is supposed to be like an abstract state space, okay? And X is supposed to be an abstract outcome space. And so therefore, the set of morphisms from S into X, these are supposed to be some set of abstract acts, like in the Savage setting, right? And we suppose that the agent has a preference order on this collection of abstract acts. And now our goal is to find something like a subjective expected utility representation for this preference order. But of course, we immediately encounter a problem because in an abstract category, what would it even mean to have a subjective expected utility representation, right? So for example, the objects in the category are not, they don't necessarily have any kind of underlying set because we're not assuming it's a concrete category. And so that means it's not really obvious how to represent beliefs using probability measures, right? Likewise, the acts, the morphisms in this category, they're not necessarily functions, okay? And even if they are, the real numbers are not necessarily an object in the category. So we can't really represent a utility function as a morphism in the category. So in other words, in general, the category is going to lack the resources that we need to sort of represent all the key components of the Savage model. So we need to be a little bit more creative in how we do this. So a little bit of sort of machinery that we need. So a partially ordered vector space is a vector space equipped with a partial order that is compatible with addition and scalar multiplication in the obvious way. So the canonical example, the real numbers are a partially ordered vector space with the obvious linear order. And given any set S, the vector space of all real valued functions on S is a partially ordered vector space under the pointwise dominance ordering. Okay, we need something with a little bit more structure. So given a partially ordered vector space V, an order unit for V is a positive element U with the property that for any other positive element V, there is some positive real number R such that R times U is bigger than V. Okay, and so a unitary partially ordered vector space is, or UPOVs, is a partially ordered vector space equipped with an order unit. So for example, the number 1 is an order unit for the real numbers. So that makes the real numbers into a unitary partially ordered vector space. And if I have a set S, then I can look at the set of all bounded real valued functions on S. So I'm going to write that as L infinity of S. So this is a unitary partially ordered vector space where the constant 1 valued function is an order unit. Okay, so this is going to be kind of like our prototype example that we keep returning to. All right, so we can make the set of unitary partially ordered vector spaces into a category in a natural way. So an order preserving linear transformation from one unitary partially ordered vector space into another is called uniferent if it sends the order unit of the first partially ordered vector space to the order unit of the second one. So let's use this notation UPOVs to denote the category of all unitary partially ordered vector spaces and uniferent order preserving linear transformations. Now suppose that C is another category. Okay, so here's the first definition. A utility frame on C is just a contravariant functor, which I'm going to write as L, from C into the category of unitary partially ordered vector spaces. All right, so here's our canonical example. Suppose we're looking at the category of sets. For any set S, let L of S be L infinity of S, the set of bounded real valued functions on S, equipped with the order unit that's the constant unit function. So for any two sets S1 and S2, and any function phi from S1 into S2, the L image of phi is just the backwards map I get by right composing with phi. So the obvious thing. So this is a contravariant functor, obviously. And so this satisfies the definition of utility frame. So the idea of a utility frame is supposed to generalize this kind of example. You're supposed to have something like this in mind when you see utility frames, right? All right, so now that we've got utility frames, we can define utility functionals. Okay, so suppose that C is a category. Let's fix a utility frame L on that category. Let F be the forgetful functor from the category of unitary partial ordered vector spaces into sets. Let's compose those together to get a functor I'm going to call L underbar and underline like this. So that's a contravariant functor from C into set. So in other words, it's sort of a pre-sheaf. Okay. Now, given any object X in the category, let's use this notation to represent the contravariant Hom functor defined by X. Okay. So given any morphism phi between two objects S1 and S2, let's write phi with a backwards arrow to indicate the image of phi under this contravariant Hom functor. So I put the backwards arrow to remind you that it's going in the backwards direction from CS2X into CS1X. Okay. So now we can define a utility functional. This is what's going to play the role of a utility function in this general framework. A utility functional for X is a natural transformation from the contravariant Hom functor defined by X into this kind of like forgotten utility frame functor. Okay, so in other words, I'm sure nobody here needs to know what a natural transformation is, but just to sort of make sure we're all on the same page, it's a collection of functions, one for every object in the category, such that basically for any object C1 and C2 and any morphism phi, this diagram commutes. Okay, so to understand why this is the right way to define utility functions in this general setting, it's the best way to illustrate that is to kind of look at an example. So here is, once this works, here is our example. Okay, suppose we're in the category of sets, and the utility frame is the L infinity functor. Let's fix some set X, and let U be a bounded real valued function on X. Okay, so for any other set C and any function alpha mapping C into X, we're going to define UCX. This is the sort of the natural transformation acting on alpha. UCX is just going to be obtained by composing alpha with U. So U composed with alpha is a bounded real value function on C. In other words, it's an element of L infinity of C. In other words, it's an element of the sort of L image of C. Okay. So by doing this, we get a function mapping the set of all morphisms from C into X into L of C. Okay. And now we can check that for any morphism phi from C1 to C2, this diagram commutes. This is easy to see. Suppose I start with some generic element alpha of the morphisms from C2 into X. Okay, when I apply the backwards map phi with backwards arrow, I get alpha composed with phi. When I then apply the natural transformation, I get U composed with alpha composed with phi, right? If I go the other way, if I start with alpha and I apply the natural transformation first, I get U composed with alpha. If I then apply the sort of pre-sheaf function down here, I get U composed with alpha composed with phi. So either way, I get U composed with alpha composed with phi. Therefore, the diagram commutes. Therefore, this is a natural transformation. In other words, a utility functional. And as most of you have probably already figured out, this example is in some sense generic, or sort of the typical example, because by the Yoneda lemma, every utility functional can be seen as a generalization of this example. So this is how we're going to represent utility functions in our categorical setting. Okay, what about probabilistic beliefs? So now suppose that C is a category and let L be a utility frame. Remember that the real numbers are a unitary partially ordered vector space where 1 is the order unit. Okay, so for any object C in the category, I'm going to define a belief about C to simply be a morphism in the category of unitary partial ordered vector spaces from L of C into the real number. So concretely, that just means rho is an order preserving linear function from L of C into the real numbers, which maps the order unit of L of C to the number 1. Okay, let's look at our favorite example. Okay, so suppose C is the category of sets and the utility frame is the L infinity functor. Okay, let's fix some set S and let mu be a probability measure on the power set of S. then we can define a linear functional in the obvious way. Rho takes any element v in L infinity of S, any function, and just maps it to the mu integral of v. Okay, so it's easy to see that this function rho is order preserving, it's linear, and it maps the constant one function to one. So it is a morphism in the category of unitary partial order vector spaces. In other words, it is a belief. Okay, so this is what the definition of belief is supposed to generalize, basically integration with respect to some probability measure in some abstract sense. Okay, so now we have all the ingredients we need to define a subjective expected utility representation. So suppose I've got two objects, S and X, in my category, and I have a weak order defined on a set of all morphisms from S into X. Let L be a utility frame on the category. So a local subjective expected utility representation for the preference order is a pair rho UX, where rho is a belief about S, and UX is a utility functional on X, such that the following expression holds for any morphisms alpha and beta. The agent prefers alpha over beta if and only if rho US X alpha is greater than or equal to rho US X beta. Okay, so let's see what that looks like in our favorite example. So suppose we're in the category of sets, and L, the utility frame is the L infinity functor. Let S and X be two sets. Let rho be a belief on S defined by some probability measure mu, like I talked about on the previous slide. Let U be a bounded real valued function on X, which defines a utility frame, U capital X, by precomposition, like I discussed earlier. So that means that for any morphism alpha, USX of alpha is just U composed with alpha, right? So that means rho of USX of alpha is just the mu integral of U composed with alpha. So that means that for any morphisms alpha and beta, this expression here, the definition of expected utility representation, just says the following. The agent prefers alpha over beta if and only if the mu integral of U composed with alpha is bigger than or equal to the mu integral of U composed with beta. So this is precisely the classic definition of a subjective expected utility representation. Okay, good. So we've achieved our first objective, but we might want to go further, okay? Because there are a few other ways that we might want to extend Savage's framework. Now, one of the first issues is the following. Savage's framework deals with a single decision problem. However, typically an agent faces many different decision problems, which might have different sources of uncertainty, so different state spaces, and they might have different menus of outcomes. So of course, we could just form a separate subjective expected utility representation for every single decision problem the agent faces, but this has two problems. First of all, it's not very parsimonious. And second of all, we would like these different expected utility representations to be somehow consistent with one another. So what we really want is some kind of grand unified expected utility representation that applies to all of these different decision problems at the same time. Closely related is an issue in modern decision theory which goes by the name of awareness. So awareness has to do with the idea that the same agent might represent a particular decision problem with greater or lesser levels of detail. So as she develops a greater understanding of her universe, maybe she represents the decision problem at a higher level of detail. She develops more awareness of it. Okay, so that means there can be multiple representations of the same decision problem. And we should have some story about how the agent kind of rationally transitions between them. Another possibility is maybe she gets access to different information sources. And the third thing is that we might want to represent analogies between different decision problems, or we might want to represent internal symmetries within a decision problem. So what we want is a generalization of the Savage framework, which satisfies these desiderata. And that's what we're going to look at right now. So this is the motivation for decision environments and ex ante preferences. All right, so what's a decision environment? So suppose that C is some category. So a decision environment on C is an ordered pair SX, where S and X are two subcategories of C. So what are these subcategories supposed to do for us? So the objects in S represent abstract state spaces. Okay, these are different possible sources of uncertainty. Of course, in an abstract category, they might not actually be spaces. So I'm going to call them state places. So for any two state places, S1 and S2, what do the state place morphisms represent? So a state place morphism from S1 into S2, you can think of that as like a C morphism from S1 into S2, which is in some way compatible with the agent's beliefs about S1 and S2 in a manner that I will explain in more detail later. But for the time being, think of it as something like a measure preserving transformation, okay? What about X? So the objects in X are abstract outcome spaces. Again, they might not literally be spaces, so I'm going to call them outcome places. What about the morphisms? Well, suppose I have two outcome places, X1 and X2. and suppose that phi is some outcome morphism between x1 and x2. That's supposed to be like a C morphism between x1 and x2 that is somehow compatible with the agent's desires over x1 and x2. It somehow preserves her desires. Again, in a way that I will explain in more detail later. Okay, so given any state place S and any outcome place X, the morphisms between S and X, these again represent abstract acts. These are the things that the agent is going to choose to do. So these are the objects of preference. So this is kind of the background. This is the setting for the decision problem. Okay, now the agent confronted with such a decision problem is going to form preferences, and that's going to happen like this. So we have some decision environment Sx. So for every state place S and every outcome place X, we suppose that the agent has a preference order, which I'm going to indicate like this, over the set of all morphisms mapping S into X. Okay, so this represents the agent's ex ante preferences over acts. Okay, so we have a collection of preference orders, not just one, we have a collection of preference orders. I'm going to bundle them all together into a big structure, which I'm going to represent with this funny triangle symbol here. Okay, so this collection of preference orders, I'm going to call it an ex ante preference structure if it satisfies two properties. The first, BP, says the following. For any state places S1 and S2, and any state place morphism phi from S1 into S2, and any outcome place X, and any acts alpha and beta mapping S2 into X, the agent prefers alpha over beta if and only if she prefers alpha composed with phi over beta composed with phi. Okay, and this is supposed to capture the idea that the state place morphisms are in some sense belief preserving. The second property is kind of dual. It says for any two outcome places X1 and X2, and any outcome place morphism phi from X1 into X2, and any state place S, and any acts alpha and beta mapping S into X1, the agent prefers alpha over beta if and only if she prefers phi composed with alpha over phi composed with beta. And this is supposed to capture the idea that the outcome place morphisms are in some sense desire preserving. Again, maybe these definitions, it's not entirely clear why that captures those ideas, but when we look at the representation, you'll see that this kind of like is exactly what we want in terms of belief preserving and desire preserving. All right, so now what we want is two things. First of all, we want to define what does a subjective expected utility representation actually mean for an ex ante preference structure defined over a decision environment in an abstract category. And second of all, once we've actually defined that, we would like to find necessary and sufficient conditions for it to exist. Now, unfortunately, due to time constraints, I'm only going to talk about the first objective in today's talk, but just trust me that the second objective is also achieved. So let's get started with this. So we're going to extend from beliefs to belief systems. So suppose that C is a category and let L be a utility frame on that category. So if you recall, that means it's a contravariant functor from C into the category of unitary partially ordered vector spaces. Let S be a subcategory of C. So for example, this could be the subcategory of state places in a decision environment. And let's use L subscript S like this to denote the restriction of the utility frame to a contravariant functor on S. So what is a belief system? A belief system is just a co-cone from this functor into the real numbers. Remember that the real numbers are an object in the category. Okay, so it's a co-cone from the functor to the real numbers. So concretely, what that means is it's a collection of morphisms, okay, i.e. beliefs, a collection of beliefs, rho sub S from L of S into the real numbers for every S in this subcategory of state places, such that for any state place morphism phi between any two state places S1 and S2, this diagram commutes. All right. So I've just pushed the definition up to the top of the slide so you can still see it. And let's look at a proposition which explains why this is the right definition of a belief system. So this is our favorite category, the category of sets, and our favorite utility frame, the L infinity functor. So suppose that S is some subcategory of the category of sets, so a subcategory of state places, and let rho sub S be a belief system on this subcategory. So the proposition says the following. For every object S in the subcategory, there is a unique finitely additive probability measure, mu sub S, on the power set of S, such that the belief rho sub S is defined by integration against mu sub S, exactly as we saw before. And furthermore, for any two objects S1 and S2 in the category, and any state place morphism phi from S1 into S2, the phi image of mu S1 is equal to mu S2. So this means that the state place morphisms are precisely the probability preserving morphisms between these different spaces equipped with their probability measures. Okay, good. So that's beliefs. Now let's talk about utility functions. So I'm running out of time, so I'm going to have to sort of go through this a bit quickly. So the key thing about utility functions is that in subjective expected utility representations, they are generally not uniquely identified. They are only identified up to positive affine transformations. So what's a positive affine transformation? So it's an increasing bijection on the real numbers of the form phi of r is equal to AR plus B, where A and B are constants and A is positive. Okay, so the set of all positive affine transformations forms a group, which I'm going to call AF under composition. And of course, we can just regard this group as a single object category in an obvious way. Now, suppose that I have some unitary partially ordered vector space V, whose order unit is 1 sub V. So a positive affine transformation of V is an order preserving bijection on V of the form phi of V is equal to AV plus B1V, where again, A and B are constants and A is positive. And the set of all positive affine transformations on V also forms a group, which I'm going to write as AF of V under composition, which is canonically isomorphic to the abstract group of abstract positive affine transformations. Okay, and so for any abstract affine transformation phi, I'm going to use phi sub V to denote the corresponding transformation of V. So why do we care about this? Well, roughly speaking, when you apply a positive affine transformation to a utility function, it's like you're changing your measurement scale. So consider temperature, right? You could measure temperature in Fahrenheit, or you could measure temperature in Celsius. The difference between Fahrenheit and Celsius is precisely a positive affine transformation. Clearly, from the point of view of physics, it doesn't matter which one you use. So any statement in physics you make in the language of Celsius, the same statement should be true in the language of Fahrenheit. And so that means that in this context here, when I talk about maximizing expected utility, those statements can only be meaningful up to a positive affine transformation. I'm explaining this verbally because I'm about to skip to the next slide. So basically, there's a way to define a utility system, a collection of utility functionals, one for every single outcome place. And these utility functionals are connected together by a network of positive affine transformations. Basically, what's going on here looks kind of like a natural transformation, but it can be made into a natural transformation, but it's kind of notationally heavy to do that, so I'm going to skip that. But the key thing is what you have now, instead of one utility functional, you have a collection of utility functionals, and every outcome morphism between two outcome places basically relates these utility functionals through a kind of a natural transformation ISK kind of diagram. But these are generated by some functor, which maps the outcome category into the category of affine transformations. Okay, this is capturing this idea of changing measurement scales. All right, there's that definition again. Maybe this example will be better. Okay, so this example will sort of make clear what's going on. So again, we're in our favorite category, the category of sets, and the utility frame is the L infinity functor. For every outcome place X, let's say U sub X is some bounded real valued function, and we define a utility functional as before. Okay, let A be a functor mapping the outcome place category into the category of affine transformations. And for any outcome places X and Y, and any outcome place morphism phi, let's suppose that U sub Y composed with phi is equal to phi hat composed with U sub X, where phi hat is the image of the morphism phi under this functor A. So phi hat is some affine function on the real number. So this is basically saying every outcome place morphism basically transforms utilities via some affine transformation. So this is what we mean by a utility system. All right, so at this point, we finally have all the ingredients we need to define a global subjective expected utility representation. So suppose I have a decision environment SX, and I have an ex ante preference structure on SX, so remember this is a collection of preference orders on the morphisms. So a global subjective expected utility representation consists of a utility frame, a belief system, and a utility system such that for any state place S and any outcome place X and any morphisms alpha and beta mapping S into X, the agent prefers alpha over beta if and only if rho S of U S X of alpha is greater than or equal to rho S U S X of beta. All right, there's an example which I'm going to skip, but it's basically just recapitulating stuff I already said. So let's just wrap it up. So basically, The remaining question is, under what conditions do these ex-ante preference structures have subjective expected utility representations? I don't have time to talk about this. Trust me, there's a characterization theorem based upon a technique which goes back to Anscombe and Aumann. And in particular, in the category of topological spaces, I can even guarantee that the utility functions are continuous and the beliefs are represented by Borel measures. But we're not going to talk about that today. Thank you very much for your attention.
You have also one question? Yes?
It's like a very tangential to this. I'm not that familiar with decision theory. So can you explain very quickly what kind of differences there are like in decision theory and like game theory? Because decision theory are not in
Yes. So decision theory involves rational decisions made by one agent. Okay. Game theory involves multiple agents interacting. In the case of decision theory, the main problem is how should this agent form beliefs, right? Basically, either probabilistic beliefs are given to you, but if they aren't, you have to do something else instead. There was a very nice talk earlier today about non-additive measures, and it started with the story about the urn with the red balls and the green balls and the yellow balls. So that's a classic decision theory setup. It's like, what do you do in that kind of a problem? In the case of game theory, you also have to form beliefs about what the other players are doing. But there you have an additional ingredient, because if you assume the other players are rational, you can use that information to place constraints on what kind of beliefs you can form about them. And furthermore, one of the questions you're asking is, what kind of beliefs are they going to form about you? And so there's this kind of notion of common belief in rationality. And so there's a lot more constraints on belief formation in the game theory context. As a matter of fact, typically in the game theory context, what you're looking for is an equilibrium where everybody's beliefs and everybody's behavior, their strategies, is consistent with the beliefs and strategies of everybody else. So that notion of equilibrium, which is central in game theory, does not exist in decision theory.
Let's think aspect again.